Okay, what I want to do today is talk a little bit about the geometry of orbits. This is the first video just talking about the shape, which is going to be an ellipse. This is decided by, or determined by Johann Kepler. Johann Kepler was a German mathematician as well as an astronomer and a astrologer. So he does believe in a little bit of the non-science of what goes on, but we'll give him the benefit of the doubt. But anyway, what he's going to do is he's going to say that orbits travel in an elliptical shape around the sun. We have a couple things called foci, and we actually have two foci to make an ellipse. We actually have the sun at one foci, and we have nothing at the other foci. So here's the sun sitting at one, here's the other foci, nothing is there. I want to show you a little bit about how you draw an ellipse. You need two pins, some string and paper, and to do that I'm going to show you part of a YouTube video called Drawing an Ellipse, and I'll let him talk.
Pull outward on the loop of string in such a way as to provide a little tension.
You notice he's already got the two pins and the string.
Keeping outward pressure so that you keep tension on the loop of string. And when you get around to the other side, you have to be careful to make sure that you
don't have to be that careful.
And if you did it right, the two ends should meet just like that.
And there's your ellipse.
An ellipse is very much like a circle.
Okay, it is very much like a circle, except that the two angles, the up and down and the side to side, the parallel and the perpendicular, are not the same. It has a couple things I want you guys to notice. It has what's called the semi-major axis, which is talking about the center of it on the way out, because we're going to use that when we start talking about things. And it actually has it right there as well as the two foci. Okay, so Johann Kepler is going to come up with three laws of motion for planetary motion. The first law is going to be the planetary law of ellipses. He comes up with the Copernican model, which says it is a heliocentric universe, or at least solar system. He said universe because he didn't know how big it was. But a sun-centered solar system, he's going to actually use that, except now he's going to describe the shape of the orbit. Remember, planets go around in a counterclockwise direction. Pick a little brighter color. Move around in a counterclockwise direction. Second law of motion. Planetary motion is equal areas in equal times. And what he basically says is, here's the sun again. And as the planet's going around in this counterclockwise direction, it sweeps out areas. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It'd be nice if you actually just had 12 of these, but let's say there were 12 of them, where the planet actually goes from this point right there to that point in a month, and then to that point in a month, and this point in a month, and that point in a month, and that point in a month. And you notice that from this point here, it's a lot larger than it is from that point. But if you look at the axis, it's a lot larger. So if you actually look at the area of these sections, they're equal. And you're going to need some calculus to figure that one out. But believe it or not, they are equal. So there's that semi-major axis again, center to the outside. Planet moves over a given interval of time. So let's say those are months. So 1 month from... And remember, this is going to be the January, so let's say this is the month of February, and this is the month of May. So month of May, we only move this far, as we're moving toward aphelion, and here at perihelion, we're moving much faster. So January would be like that distance, and if you'd look at that distance and compare it to this one, it would be the same as well. His third law is called the Harmonic Law. It's the square of the planet's orbit. And basically what you do is you take the period of time that the planet takes to go around the sun, and you square it, and you take the distance, AU value, between the sun and the planet, and you cube it, they're the same number. And what I want to do is show you Jupiter's. Jupiter has an R value of 5.2, and if we cube that, 5 cubed is 125, so a little more than that. Let's say it's 140. I'm going to say 144 just because that's a nice clean number. So what I did is I actually cubed that number, and it's equal to the square. And you guys know what the square root of 144 is? It's 12. And it takes Jupiter 12 Earth years to get around the Sun. And you can do this with every other planet. You can do this with the Moon. You can do it with satellites. You can do it with stars going around the Milky Way galaxy. It's a way of actually calculating how long it takes an object to orbit another object. And again, that's Kepler's third law. Pretty amazing fact way back when. Example of ellipses. Ellipses are actually given what's called eccentricity. An E value of 0, an eccentricity value of 0 is a nice perfect circle. In other words, the two values up and down, side to side, are the same. If you do an E value of 0.23, you start seeing that this horizontal value enlarges, and the vertical gets smaller. An E value of 1 would be a straight line. Because what you'd get is you'd have your two foci so far apart. All you'd be able to do with that string is to nice line, move it straight across. And if you take a look, Mercury has an eccentricity of 0.206, really close to this, pretty round. Venus, closer to this. Earth, I guess still closer to that, somewhere around it. Who's got the roundest of all the orbits? Do you guys agree? Ka-ching! Who's got the least round of all the orbits? Ka-ching! And that's one of the reasons why Pluto got taken out of the whole idea of planets. Now Mercury's got the least round, even though it is still fairly round. We don't have any planets with a 0.77. We will have galaxies that are like that when we start talking about galaxies. Okay, so we have Mercury going around the Sun, Venus going around the Sun. Remember, they're all going around in counterclockwise directions. Venus is going around much faster. Sort of like the whole idea of Kepler's second law. The closer you are to the Sun, the faster you move. Venus moves not as fast, but faster than the Earth, who moves faster than Mars. If you looked at them from the side, you can see Mars's orbit is tilted a little bit more than the other three, even though the other threes are tilted. And we did talk about the Earth being, actually we call the Earth as being nice and flat. The actual planet is tilted, but the other planets are tilted more or less in comparison to us. And then if you look at on the outside, you got Mars in there. You have Jupiter going around, which moves a little. Where is Jupiter? Jupiter moves around, but moves a little slower than Mars did. Saturn moves a little slower. Uranus, even slower. Neptune, the slowest of all the major planets. And here's another problem with Pluto. Between 1999, I think 79, between 1979 and 1999, for those 20 years, Pluto was actually closer to the Sun than Neptune. And we can't have planets crossing each other's orbits. And then the last thing, if you look down here, eccentricity of planets. Venus is the roundest of all the planets. Pluto would be the least round. Mercury is the least round of the planets as of today. Earth is pretty round. Neptune's pretty round. And you can see there's a little bit of difference. Okay, so orbit of the planets, ellipses, eccentricity, how elliptical are you, and then Kepler's three laws. One to say it is an ellipse, two to actually say it's equal measure, sweeps out equal areas in a given time, and third actually uses the values for distance to determine time it goes around the sun, or the time it goes around to figure out the distance. And that works for other things too. Thank you much. Bye.